On slide 5, I described some earlier research related to our topic. And Greenberg-Kessler in 1982 wrote an interesting article in Sociological Methods and Research where they considered a model with cross-lagged effects and reciprocal effects, also relating to previous sociological and econometric modeling in that area. And they showed that identification could be achieved by imposing a certain degree of time invariance. However, at the end, they provided some disappointing conclusions. These results are discouraging. The approach can be used in practice under a very restricted set of circumstances. So the idea of this modeling does not seem to have been picked up in practice. You haven't seen that in applications. Well, not until 20 years later, where Ormel and others published an article in Journal of Gerontology where they considered a model estimated with both cross-lagged and reciprocal effects, as well as random intercepts. They, however, gave no proof of identification. They claimed that the model is identified, and they made that claim mainly or only because they got the same solution when trying different starting values. So 20 years after Ormel then, 40 years after Greenberg-Kessler, we have a paper looking at this again and trying to see how practical is it to do this sort of analysis. On slide 6 then, we point out that there are really two common types of question formats in panel data measurement, and that influences the modeling that we actually should consider. There are past status questions in the last time intervals, like 30 days, last year, how frequently did you something, and current status, how much do you agree with this statement? And that current status could be right now, or it could be experiences that you've had for a while. We're going to take a look at some data sets from this article by Ort in 2021, where he provided the data freely for use. And it's in his paper, there are 6 data sets with various time intervals between measurements: 2 months, 6 months, 1 year, and 2 years. And my claim here is that cross-lagged effects may be less realistic with long time intervals and may call for allowing contemporaneous lag zero effects. Interestingly, the choice of distances between measurements, the time intervals, was considered in this Dormer and Griffin article that Ellen Hammacher recommended to me about optimal time lags in panel studies and how the results, of course, depend on the time lags. They also provide an algebraic method to explore the optimal choice. It relates a bit to the DeBook and Preacher paper on mediation analysis, similarly considering the effect of time interval between measurements. On slide 7 then, we can consider 2 competing panel models. On the left is the standard cross-lag panel model with in the form of CLPM for 2 time points. And imagine then at the second time point here we have a question that refers to experiences in the last year. So that the measurement at the time point earlier refers to 1 year back from that time. So you can imagine then that an experience could happen in the beginning of this time frame, and the key event for time point 2 happens at the end of that year, and then there would be a cross-lagged effect that refers to 2 years. So the cross-lagged effects of events between 1 and 2 years ago, I argue, may be weak. Instead, the reciprocal lag zero model on the right may be more realistic when you have these long time intervals and measurements referring to past experiences. So the difference is that we don't have these cross-lagged effects anymore. Instead, we have a reciprocal interaction here, this variable influencing that, and that variable influencing this. The reciprocal model is identified by the classic econometric rule that each reciprocal dependent variable has its own predictor. This variable is only influenced by that variable, not the other one, and likewise for this. And this kind of model and the debate between using this model or that model is a long-standing debate in the classic econometrics, going back to a series of Norwegian researchers in the 1940s, I believe. Now, the two models are actually equivalent and can't be statistically distinguished. You have the same number of parameters. Here you have 1, 2, 3, 4 regression parameters. Here you have 1, 2, 3, 4 regression parameters as well. And you have one residual covariance, and at time 1 you have this correlation between the variables. So same number of parameters, same model fit to data. So finding cross-lagged effects by this model on the left, the red model, does not therefore rule out the reciprocal model, and finding reciprocal effects in this model on the right does not rule out the cross-lagged model. So we have model equivalence here. On slide 8 then, the model on the right may actually then be considered as a summary of several sets of cross-lagged effects, these green arrows here going on across time. But we don't measure them. We don't measure frequently enough here to capture them. We only measure here and here, 1 year apart in this example. So thereby we don't disentangle the recursive causal effects, the green arrows, because we didn't measure frequently enough. And to some, that may be therefore a negative. That is, we would like to find these causal effects, quote unquote, that is, effects that are of the kind that something happens at one time point influencing something else at a later time point. You don't get that quality of conclusion from the reciprocal model here. So the question is, on slide 9, can we include both cross-classified and reciprocal effects in a model? Well, here's a model then for 2 time points again. And we have 6 regression coefficients, 1, 2, 3, 4, 5, 6, but only 5 sample covariances. This covaried with that, this covaried with this and that, and these 2 covarying. We can ignore this covariance back there that has its own parameter. So we try to estimate 6 parameters from only 5 sample quantities, so that is not identified. But the interesting thing is that the model is identifiable when we have more than 2 time points. So there is the sequence of Greenberg-Kessler 1982, Ormel 22, and Mutean 2022, and Asparov. Now, if you consider the reciprocal cross-lag panel model for 3 time points, it would look like this, where the model is identified if you have equal reciprocal effects across time 2 and 3. So this is the reciprocal effect going from below to the above variable, and that has the same value across time invariance. Likewise, for the arrow going the other direction, you have the parameter c. So you impose 2 restrictions here, and that makes the model identified. Now, I should also mention that adding random intercepts to this model does not affect the identification status at all. In the random intercept model, this would be the within part of the model, and the identification really concerns that part of the model, as discussed in the Asparov-Mutean paper. Now, the model is not identified if all of the parameters are time invariant. So a reciprocal DSEM is not possible. This time series model where we assume time invariance for every parameter. So that's not possible. It's not possible to do a reciprocal combined with cross-lagged model in that setting. Now this model also has some issues. There are special considerations that are needed in the analysis, and we'll get to that in a moment. On slide 11, we can take a little deeper look at these two alternatives, the CLPM on the left and the reciprocal CLPM on the right. And once again, we could have a random intercept version of it, but this is simpler to draw. So if you look at the model on the left here, the residual covariances, they allow time-varying, unmeasured common causes to influence the two outcomes. So time-varying, unmeasured causes come in here to the residuals, and they're common, so they correlate. So we allow that by that residual covariance. While on the other hand, on the right, in model B, the two outcomes, the residuals of the two outcomes are uncorrelated. Covariances are zero, no covariances here. So one can think that that's a disadvantage of the model on the right, but in line with regular regression, model A also makes strong assumptions. Model A assumes that the residuals are uncorrelated with the two predictors. So these residuals are uncorrelated with the predictor here and here in the influence on this variable. And that's a strong assumption. And if it's not true, that's a standard assumption of linear regression. If it's not true, the cross-lagged effects will be biased. So if the data have actually been generated by model B here, the model A residuals are correlated with the predictors because each outcome at time t is influenced by the other variable at time t. So each outcome here at time t is influenced by the other variable. So there is another cause, another predictor, which is correlated with the two predictors, and therefore the assumption in model A is incorrect. So there are then pros and cons of these two models. They come with their own set of assumptions, and we therefore, it behooves us to look at both of the models. On slide 12 then, I put up all three models here for 3 time points and point out that they are equivalent models. So at the top we have for three time points the classic CLPM model, and in the middle we have the what I will call the reciprocal only model. So you have no cross-lagged effects. You still have the covariances between the residuals. And at the bottom we have the model that I simply call reciprocal, where you have cross-lagged effects just like in the top model, and you have the reciprocal effects with time invariance, but you don't have the residual covariances that you have in the two models above it. So these three models are totally equivalent. They have the same number of parameters, and they fit the data the same. So the bottom model here is an equally valid model as the model at the top, and so is the middle model. These two models, the middle model and the bottom model, provide an alternative interpretation of the data than what is obtained by the classic model at the top.